Alright, what are ferromagnetic materials? Ferro is iron, is that right? Now, these materials exhibit a strong attraction to magnetic fields and are able to retain their magnetic properties after external field has been removed. That means they will respond to the external magnetic field very strongly, and the domains will align themselves to a very large degree. And even when the external field is removed, some of the alignment will be retained. Such a material is a ferromagnetic material. They are very good magnetic materials. Now, in the domains of these materials, large numbers of atomic moments of the order of 10 to the 12 to 10 to the 15 are aligned parallel so that the magnetic force within the domain is very strong. In the unmagnetized state, the magnetic moments of the domains are randomly oriented, and when a magnetizing force is applied, the domains become aligned, producing a strong magnetic field within that material. Now, the permeability mu of a ferromagnetic material actually depends on the strength of the external magnetizing field. So there is no particular value you can assign to a ferromagnetic material. What that means is mu for a ferromagnetic material is not a fixed value. It depends on the external magnetizing material. Examples are iron, nickel, cobalt, and so on. What are paramagnetic materials? Well, these are materials which will respond to a certain degree, but the extent of magnetization is not very strong. Now, the paramagnetic properties are again due to the presence of some unpaired electrons and from the realignment of the electron orbits caused by the external field. And they have permeability values slightly greater than mu0, the permeability of free space. Not very strongly magnetic. And these materials include magnesium, molybdenum, lithium, and tantalum, and so on. How about diamagnetic materials? These are materials that exhibit actually a negative magnetism. Well, diamagnetic materials are slightly repelled by magnetic field, and the material does not retain the magnetic properties when the external field is removed. Diamagnetic materials are solids with all paired electrons, resulting in no permanent net magnetic moment. Now, we have examples of that will be most of the materials that we know, copper, silver, gold, they're all diamagnetic, and their permeability will be slightly less than mu0. Alright, so we have ferromagnetic materials who have no fixed permeability value. Diamagnetic materials have permeability values less than mu0, paramagnetic slightly greater than mu0. And this leads us to another important term in magnetism, that is magnetic susceptibility. Alright, we know that all materials exhibit magnetism to some extent. The value of the magnetic permeability mu of a material determines the extent to which a material acquires magnetism in the presence of an external field. Is that right? Well, therefore, the ratio of mu divided by mu0, permeability of the material divided by permeability of free space, is an important term, and it is called a relative permeability. It actually compares the magnetic properties of a material with that of free space. So what is relative permeability? It is mu divided by mu0, and we represent relative permeability by K sub m. So K sub m is mu divided by mu0. Now tell me, for a paramagnetic material, because mu is slightly greater than mu 0, Km is slightly greater than 1. But for paramagnetic, it is slightly less than 1. Is that right? Now, the magnetic susceptibility, Km, susceptibility is represented by the Greek letter. Look at the way I read it, chi sub m, Km. Now, we use Km to define Km as Km equal to Km minus 1. Magnetic susceptibility equal to the relative permeability minus 1. Now that means paramagnetic substances have Km slightly greater than 1. Therefore, the susceptibility of a paramagnetic material is positive. How about diamagnetic materials? Their Km is slightly less than 1. Therefore, Km will be negative. How about ferromagnetic materials? Well, they have positive susceptibility, but they have no fixed values because the permeability depends on the external magnetizing field. Well, that brings us to the end of this lesson with a discussion on hysteresis loop. What does that talk about? It talks about the way we magnetize a material. In order to magnetize a material, we use a magnetizing field. You see, if I bring a magnet close to a magnetic material, the magnetic material becomes a magnet. Now, here is a magnetic material. This is not a magnet, but this is a magnet. I can magnetize this by subjecting this to a magnetic field. You can see as I bring it closer and closer, the extent of magnetization in this material will increase. Now, as I bring it closer, I can feel it. It's actually pulling me. So, the extent of magnetization, that means the magnetic flux that is created in here is, well, increases as the magnetizing force increases. So the magnetization of a magnetic material increases as the magnetizing force increases. Now, hysteresis loop is actually a diagram that shows the amount of magnetization in a magnetic material compared to the external magnetizing field. Now you can see how strong it is. Now, mostly the external magnetizing field is changed by using an electric current. So a plot of induced magnetic flux B, the magnetic flux generated in the magnetic material, versus the magnetizing force H is called the hysteresis loop. And here I have a diagram of that. Now we're going to start here, where the magnetizing force is 0 and the flux, the induced magnetic flux also is 0. So that's the situation that we actually started with. Now, this is so strong. Now, if it is so far, that is where we are here. Now, I'm going to increase the magnetizing force. The magnetizing force increases, the induced magnetic flux also increases. Now, so this is where we start, and we increase the magnetizing force, the magnetic flux induced increases, and this is the path until we reach a saturation point. What does saturation mean? All the magnetic domains are aligned, and it has reached a saturation, and you cannot attain any more magnetization. Now, if you decrease the magnetizing force, now what happens? The aligned magnetic domains will begin to disalign, and when the magnetizing force is 0, the induced magnetization does not return to 0. a certain amount of magnetism is retained. So for a particular value of H, the magnetic flux density reaches a saturation value. If now H is reduced, B will also be reduced, but not along the same path. That means certain amount of magnetism is retained. When H is 0, that is H is brought back to 0, the curve will move from point A to point B. At this point, it can be seen that some magnetic flux remains in the material, even though magnetizing force is 0. Now remember, this discussion is purely for ferromagnetic materials, which retain some magnetism even when the magnetizing force is removed. What happens if you now increase the magnetizing force in the negative direction? Now, as I told you, the magnetizing force is actually a current. If you pass current in one direction, you have magnetizing force in one direction. If you reverse the current, you have a reverse magnetizing force. If you reverse the magnetizing force, the domains are brought back to 0. That means the magnetization here is 0. But it's 0 not when the magnetizing force is 0. So let's talk about this before we come to that. What do you call this point? This is the point where the magnetizing force is 0, but certain amount of magnetization is retained. We call that point the point of retentivity. Alright. As the magnetizing force is reversed, the curve moves to a point C where the flux has been now reduced to 0. Now, this is called the point of coercivity. That means the reverse to magnetizing force has flipped enough of the domains so that the net flux in the material is now 0. The force required, what's this one? The force required to move the residual magnetism from the material to 0 is called the coercive force. The coercive force is the force required to move the residual magnetism back to 0. And that's why this is called the coercivity. And now, if the magnetizing force is sufficiently increased in the negative direction, then all the domains will be aligned in the opposite direction and will reach saturation. And you can retrace that path. So reducing H to 0, bring the curve back to E, and then increasing H in the positive direction will return it to point F, and of course the loop can be completed. Now you can see the loop does not really follow the same path. Well, that actually clearly indicates about the retentivity of magnetism of a ferromagnetic materials. Well, I'm going to stop this lesson here, and we will talk more about magnetism and properties of magnets in the next lesson.